Well, I just wanted to say thank you, and what an honour it is to speak at this important event for honouring Trevor Pearcey, a great Australian and a real pioneer of computing technologies. Also a great pleasure to be sharing a podium today with very long-term collaborator and colleague David Riley. So in my talk today, I'm going to aim to give you an overview of where quantum computing is today, what the fundamentals of quantum computing are, what the key applications are, and also where some of the challenges lie. So, but I want to begin with SCI Rack and Trevor Pearcey, because the SCI Rack and computers like it were obviously great trailblazers for the computers that we're used to today. This system, as many of you would know, was operated using vacuum tube technology, and so therefore to produce the equivalent of a small calculator, it required effectively 2 rooms full of many vacuum tubes, consuming a lot of power and obviously a great deal of space. And of course, as you were all also aware, the stage beyond that was to miniaturize by using solid-state devices. So the invention of the germanium and silicon transistors and the silicon integrated circuit allowed this progression, now known, of course, as Moore's law, of a massive increase in the number of transistor elements, computing elements, bits that can be crammed onto a square centimetre of silicon. Rising from around 1,000 in the 1970s up to now the many billions today. And so while the technology that Trevor Pearcey and others around the world developed was very modest in terms of computing power compared to what the Silicon Revolution provided, the concepts and the understanding of programming and understanding how to program a computer was an absolute trailblazer, which really made this next generation of technology possible. And I think that's a theme that I'm going to return to at the end of my talk. So as existing CMOS technology is already at the point where the gate lengths, the feature sizes of basic transistors is already of order 10 nanometers. And if Moore's law were to continue in terms of reduction of transistor size, it would only be another decade or so before an individual transistor was at atomic dimensions, at which point basic MOSFET action would fail. Now, the way that the industry is getting around this is by now making multi-core processors, because there is ultimately a limit to how small those transistors can be. And certainly there are many generations of optimization using CMOS technology that we can look forward to. However, in 1982, Nobel Prize winner Richard Feynman, pictured here on the screen, was invited to give a talk about where he saw the future of computing at the time, given the fact that integrated circuit technology was already prevalent. He was asked, how small could these transistors be? How far could it go? And in a very famous lecture series in which he titled his paper "Plenty of Room at the Bottom," he noted that the ultimate type of computing would potentially be to use individual atoms or individual quantum particles to do computing. The idea here being, for example, to use the ground state and first excited state of some quantum system, like the internal energy levels of an atom or ion, to define the bits the bit states 0 and 1, or in this case, we see a particle containing a spin, such as an electron, where its magnetic moment can be aligned or anti-aligned to a magnetic field, again, to define the 0 and 1 states of a basic bit, but now on a quantum system. Now, Feynman recognized that the potential benefit of this is that quantum states can exist in superpositions. They can also have a phase associated with them, which gives them much greater storage information capacity than a conventional bit. And he prophesied right back then the idea that only quantum bits would be able to simulate a real physical quantum system, which has that wide range of possibilities of quantum phase and amplitude. That issue of quantum simulation is something that is the very first quantum computers today are looking to challenge as one of their first tasks. So the main advantages of these quantum bits then is that it's possible to store far more information in them, but manipulating them, reading out the information and performing algorithms on those is a significant challenge. And in fact, there is a range of different application areas where quantum computers can have an advantage over conventional computers. And I'm just going to go through really some of the main ones on this slide. So the first one that I mentioned is one that really motivated a lot of investment in quantum computing, and this is decryption. So public key encryption, which we use to send all of our credit card details when we do online purchases, is protected by a coding called public key encryption, as many of you would know. The heart and the unbreakability of public key encryption relies on the fact that there is a public key, which is a very large composite number made up of 2 primes. Factorizing those 2 primes is a very difficult problem, effectively impossible for the length of key that's used in modern day codes. But Peter Shaw, a computer scientist at Bell Labs, showed that on a quantum computer it would be possible to factorize that large composite into its primes in polynomial time rather than exponential time on an existing computer. So decryption was really one of the first areas of quantum algorithms that was identified, and it stimulated a lot of investment for national security agencies and so on. But it's not necessarily a particularly valuable thing from a commercial perspective. An area that's much more valuable and important is the area of data mining and storage. So 2 years after Shaw invented his algorithm, in 1996, Lov Grover developed an algorithm to show the significant quantum speed up possible in searching a very, very large database. And the photo at the top left is actually a Facebook data center that's located in the Arctic Circle. The purpose of putting it in the Arctic Circle is because the amount of heat generated in the huge arrays of processors and memory systems used to store everybody's Facebook information and then to search it is a very, very significant amount of energy and power consumption. And so a lot of cooling is required. And so part of the solution of that in this data center is to put it in an environment that's already very cold outside. Quantum computers will ultimately be able to speed up the data mining and also reduce that energy consumption. Another area where quantum computers are known to have an advantage is in the area of optimization. This is effectively in solving problems, routing problems, scheduling problems. And these obviously has a broad range of commercial applications to distribution networks, to parcel delivery services, airlines, etc. And the last example I want to give actually comes back again to the original idea by Feynman, and that is one of quantum simulation, whereby a quantum computer is uniquely configured in order to simulate a real physical system. Now, you may know that already quantum chemists, for example, are using supercomputers to try to simulate the properties of molecules, proteins, and so on. But this begins to become effectively an exponentially difficult problem if one wants to obtain the full details of the energy states, the folding states of the proteins, etc., as a molecule becomes larger. Effectively, in order to simulate on a conventional supercomputer, even a molecule as large as, say, 44 atoms already becomes intractable. So the area of designing new molecular systems, potentially new pharmaceuticals, even new materials using a quantum computer is really one of the most exciting future prospects. So given those exciting prospects, let's now have a look at what the key quantum computing technologies that are around today are to realize these two-level quantum systems. So one that is certainly most advanced in terms of numbers of qubits on chip is using superconducting circuit technology. So a range of both companies and universities are pushing this forward. I'm going to give you a scale of where these different technologies are at the end of the talk, but certainly superconducting qubits are at the moment the most advanced, effectively neck and neck with the technology that had been ahead of it for some time, and this is ion trap qubits. So ion traps effectively comes from atomic clock technology, where one can exquisitely control with laser pulses the internal states of ions trapped in an electromagnetic field. Pictured there is David Wineland, who won the Nobel Prize for his work in this area a few years ago. Other technologies that are important, for example, are using diamond spin states in diamond, which can be optically addressed. These have the advantage of operating at higher temperatures, and also photon-based qubits using effectively photonic technology and encoding information in the polarization of the photons. Finally, an area I'm going to talk about in a little bit more detail now is silicon qubits. This is an area of my own research and a significant effort in Australia. The motivation here is to effectively utilize the scalability of the technology that, of course, has enabled the computer industry today. So here are some images of what modern day real quantum computing systems look like. The most advanced, in particular, superconducting systems like silicon have to be refrigerated down to low temperatures of typically below 1 Kelvin. And so these show images of dilution refrigerators, of which there are many, in fact, in this building here, including examples from IBM, D-Wave, and Google. So coming now to who the major commercial investors in this are. In the area of superconducting qubits, Google, IBM, and also a Canadian startup, D-Wave, have the most significant investments. Microsoft, as we're about to hear in the next talk from David Riley, are investing heavily in a new type of quantum computing called topological quantum computing, using particles known as Majorana fermions, which I'm sure David will speak more about next. Intel are having something of an each-way bet. They're investing in both superconducting qubits and in silicon qubits. And here in Australia, many of you may be aware of the company Silicon Quantum Computing, which has been formed from the Australian and state governments, plus Telstra and CBA, with UNSW to commercialise the silicon quantum computing work being done in Australia. So coming now to Australia's position, where it is, thinking about the great work of Pearcey, how is Australia positioned for this next generation of computing? Well, in fact, Australia was the place where the first concept for a silicon quantum computer was made. That was at UNSW by Bruce Kane, who first conceived of the idea of using, in fact, single phosphorus atoms embedded in silicon as spin qubits. And the motivation for that was that the quantum coherence time, the information by which the information remains faithful without being scrambled, was known to be very long for spin states in silicon. And the other advantage, of course, is the manufacturability and industry compatibility, which can ultimately then allow scaling up that technology. And very soon after Kane's original scheme, Bob Clark, who was a professor at UNSW, founded a national centre, initially with 3 universities, UNSW, Queensland and Melbourne, but then expanded to include University of Sydney, Macquarie and others. This national centre really was the first one in the world that took such a national perspective to try to advance quantum computing. After Bob Clark left to become Chief Defence Scientist of Australia, Gerard Milburn took over as director, and then the centre was expanded to also include quantum communication technologies. And of course, the director these days, since 2011, is Michelle Simmons, who I'm sure people are aware was the Australian of the Year last year for her work. In parallel, another major centre in engineered quantum systems, EQUIS, was established initially by Gerard Milburn, who spawned a completely new centre with a number of very young, up-and-coming people who had, many of whom had come out of the previous centre. This centre is now led by Andrew White, and there are many leading chief investigators and professors here at the University of Sydney who are part of that centre, including Professor Bartlett, Professor Flamea, and David Riley himself. So in terms of doing what we heard from our chief scientist in New South Wales, actually taking this great science and commercializing it. I just want to briefly talk about what is being done in Australia. So I already mentioned the company Silicon Quantum Computing, which is commercializing the technologies that originally came out of UNSW and its partners. Next, you're going to hear from David Riley, who, as part of an international consortium, has made Australia a major player in the effort of Microsoft, really managed to attract very, very significant investments in Australia from that from a major multinational. And also here at the University of Sydney, we have Mike Biersook, who set up a company, Q Control, with venture capital investments to develop software to improve quantum systems. In the last minutes, I just want to show a little bit about where silicon quantum computing technology is. The computers that we use today, of course, based on the MOSFET transistor. This is an image from some years ago of a MOSFET on a Pentium processor. The basic structure uses this gate electrode to induce electrons in the silicon channel below. In 2014, we were able to show that we could reduce a MOSFET transistor down to the level of just one electron and then use the spin of that electron. And what you see below are so-called Rabi oscillations, where one is controlling the spin state from down a logical 0 to an up a logical 1 with very, very high precision and control. Since that time, our group at UNSW, with this CMOS approach, I want to, in contrast with the phosphorus atom approach that had been proposed by Kane, using the CMOS approach, it's possible to form a 2-qubit logic with this. And with 1 and 2 qubit logic, one is then able to effectively perform any calculations, just as one can with inverter gates and NAND gates on a conventional computer. And so, because of the benefits of using CMOS, we've been able to design a full detailed architecture for a CMOS-based quantum computer using these quantum dot qubits, including full bit and word addressing schemes to operate the system. Just to visualize this, what's going on there? A MOSFET today uses electrons running from a source to a drain electrode. What we're looking to do is to reduce those to 1 electron, as we recently demonstrated, manipulate it with microwave and with electric fields to perform 1 and 2 qubit logic, and then create a 2-dimensional array which can be manipulated by control gates on a word and bit basis, much like conventional CMOS transistors are today. So my final slide, I just want to leave us with where quantum computing is and what are the biggest challenges. Well, the biggest challenge for quantum computing is that qubits are very fragile. They're very susceptible to noise. They've got a terrible noise margin. And so in order to protect that, we have to put many physical qubits together in what's known as a logical qubit using quantum error correction codes. And to solve the big grand challenge problems I talked about earlier, like pharmaceutical design, decryption, it's essential that quantum error correction is involved. But those sort of problems require at least hundreds of logical qubits, which means that the physical qubit number is somewhere in the millions to billions. So it's a very, very significant challenge. Today, in contrast, Google is working on a 72-qubit system. IBM has around 20 that they've made publicly available. A company in the US, IonQ, working in ion traps, has 11 fully connected qubits. In the silicon world, we're still at 2. So small scale, but as I'll mention in a moment, the aim is that to utilize the scalability of the technology, it'll be possible to leapfrog the other technologies. So it's expected that a logical qubit was going to be probably demonstrated in the next 1 to 2 years. But a logical qubit is really just one piece of memory element. It doesn't actually do anything. So today, people are focusing over the next few years on what's called noisy intermediate scale quantum computing. And I reference this paper by John Preskill, one of the founders of quantum error correction, who came up with this term. The idea here is that rather than doing error correction, one deals with noisy qubits and tries to do as much computing as can be done before the information gets scrambled. One key milestone that's being targeted this year by Google and others is to demonstrate a thing called quantum supremacy or quantum advantage, which is the point when operations are done on a quantum system that cannot be done even on any supercomputer in the world today. And over the next few years, the aim of efforts around the world is to do simulations of the type originally proposed by Feynman of molecules to solve simple algorithms, simple problems. And so finally, I just want to leave you with the message that these near-term quantum computers of today are a little bit like Pearcey's computer back in the late 1940s. Not necessarily the ultimate computers that are going to be used, because they can be large, they have a number of overheads and so on. But hopefully, with advances in technology, CMOS technology applied to quantum computing, it'll be possible to make quantum computers practical and to solve some of those grand challenges I talked about earlier. Thank you very much.